In this video, we're going to review how to draw a Lewis structure because a lot of different skill sets in chemistry are based on drawing a correct Lewis structure. So we're going to start by looking at a few atoms that come up very frequently in Lewis structures and determine the number of bonds that they need to make in order to complete their octet. Keep in mind that hydrogen is one of the exceptions to the rule. It does not need to have 8 electrons, it only wants 2 electrons. Because hydrogen has 1 electron, and if it gains another one, it's going to have the same electron configuration as helium, and that will make it very stable and happy. So hydrogen wants to have 2 electrons total. Notice that it's in group 1A, which means that hydrogen has 1 electron. In fact, everything in this group has 1 valence electron. And these are all valence electrons specifically that we're referring to. So since hydrogen has 1 valence electron and it needs 2, it needs to make 1 bond with some other atom in order to complete its version of an octet, which is really a duet. It wants 2 electrons. Boron is another one of those exceptions. It wants 6 valence electrons. And if we look at where it is in the periodic table, it's in group 3A, which means it currently has 3 valence electrons. So in order to have 6 electrons, it needs to gain another 3 to complete its version of an octet, which is 6 valence electrons. The rest of these follow the standard octet rule. So carbon wants to have 8 valence electrons. It is in group 4A, which means it has 4 valence electrons and needs to gain another 4 in order to complete an octet. So carbon will typically make 4 bonds. Nitrogen is in group 5A, so it has 5 valence electrons, and it needs to gain 3 in order to complete its octet, so it will make 3 bonds. Using the same logic, oxygen is in group 6A, so it needs 2 valence electrons, and all of the halogens are in group 7A. They all currently have 7 valence electrons, and they need 1 more to complete their octet. So it's a good idea to know for these select atoms how many bonds they typically make, and if you ever forget, you can sort of reason your way through it using the same logic that we just did. Once we have that information, the first thing we're going to do is place the atom that wants the most bonds in the middle of the structure. So the atom that wants the most bonds will be the central atom. Usually this is the atom that there is the least of in a particular formula, but that's not always the case. The second thing we're going to do is determine the total number of valence electrons for the entire structure by counting the valence electrons that each atom in the formula contributes. So let's try these first 2 things on this particular formula. That's the formula of ammonia. So the first thing I'm going to do is figure out which atom is central. Keep in mind that nitrogen wants to make 3 bonds, whereas hydrogen only wants 1. So hydrogen and halogens are typically not going to be in the center of the molecule. In fact, hydrogen will never be the central atom. It is impossible. So I'm going to put nitrogen in the middle, and then I'll draw hydrogens around it. Using rule number 2, I need to figure out how many valence electrons are present in that entire structure. And for that, I'm going to count how many valence electrons each atom contributes. Looking at the periodic table, nitrogen contains 5 valence electrons. And hydrogen contains 1 valence electron. Now notice, looking at the subscript, that there are 3 hydrogens in that chemical formula, and we need to account for that when we're counting our electrons. So I'm going to multiply the number of electrons that hydrogen brings by 3, which gives us 3 electrons in the formula. And then we're going to add all of that up, and the total number of valence electrons in this structure is 8. Now that we have that information, we need to think about how we're actually going to connect these atoms to each other to form bonds. So the third thing we're going to do is attach each atom to the central atom by a single bond. So we'll start with single bonds and kind of go from there. Keep in mind that a single bond represents a pair of electrons. So when two atoms come together, and I'm going to simplify this, let's say two hydrogens come together, each of them has 1 electron. If they pair up, they share those electrons to complete their duets, and we represent that just by drawing a line. So each line that you draw represents 2 valence electrons. So looking at that in the previous structure, I'm going to connect the hydrogens to the nitrogen using a single bond. And if we count how many electrons we used, well, this bond used 2 electrons, this bond used 2 electrons, and this bond used 2 electrons, which means that overall we have used 6 valence electrons. And keep in mind we have 8 total. So we used 6 out of 8. We need to figure out what we're going to do with those remaining electrons. And that brings us to the next rule. If there are remaining electrons, use them to complete octets. So we're going to distribute them to the atoms that need them in order to fulfill their octet. So if we look at this right now, well, hydrogen has access to 2 valence electrons, and each hydrogen is happy with that. It only wants 2 valence electrons. Nitrogen right now is not particularly happy because it has access to 6 valence electrons, but it needs 8. And everything is already connected by a bond, so I'm going to distribute the remaining 2 electrons to nitrogen as a lone pair of electrons. And now that I look at that, well, now nitrogen has access to 8 valence electrons, and this structure is good to go. So the next thing you always want to do is make sure that every atom in the formula has the number of valence electrons that it needs. In some scenarios, you could run out of valence electrons, but you still need to complete octets. And in that case, so if the remaining electrons do not complete the necessary octets, then we will draw double or triple bonds to compensate for that. For example, let's draw let's draw the Lewis structure of HCN. So the way that this formula is drawn kind of gives you a hint as to which atom needs to be in the center. But if you're not sure, we can go back and think about this. Hydrogen only needs 1 valence electron, so that is only going to make 1 bond. Then carbon needs 4 bonds in order to complete its octet. Nitrogen needs 3 bonds to complete its octet. Since carbon needs the most bonds, we're going to place carbon in the middle and then connect the remaining atoms around it. The next thing we're going to do is calculate how many valence electrons are present in the total formula. Hydrogen has 1 valence electron, carbon has 4 valence electrons, and nitrogen has 5 valence electrons. And these numbers, of course, come from the periodic table. Nitrogen is in group 5A, so that's where 5 valence electrons come from. Carbon has 4 valence electrons because it's in group 4a, and hydrogen has 1 valence electron because it's in group 1a. Now we have one of each in the formula, so we don't need to multiply anything. We're just going to add these numbers up, and the total number of valence electrons in the formula is 10. So using rule number 3, I'm going to start by drawing single bonds. And this used 4 valence electrons so far. So 2 electrons in this bond, 2 electrons in this bond. We still have lots more valence electrons to go. So we used 4, we have 6 more that we can distribute. So I could start by trying to fulfill the octets of the remaining atoms. Hydrogen is happy right now. So I'm going to give the remainder to nitrogen that used up all of my electrons. So I have 4 electrons in these bonds and then 6 electrons in the lone pairs. But notice right now that I've used all of the electrons available, but carbon does not have an octet. Nitrogen is happy, hydrogen is happy, but carbon only has 4 electrons and it needs 8. And I can't add any more electrons because I've already used up all of the ones that are available. So what I'm going to do is I'm going to take the 2 lone pairs of electrons from nitrogen and use them to make a double bond. This helps. Carbon now has access to 6 valence electrons, but it's not quite happy with that either. So I'm going to take the remaining lone pair of electrons from nitrogen and use that to make a double bond. And now we have a triple bond, and I'm going to go through and make sure that every atom contains the electrons that it needs. Hydrogen has an access to 2 valence electrons, and that's exactly what it needs. So hydrogen is happy. Nitrogen has 2 valence electrons in this lone pair, but then it has access to 6 electrons in the triple bond, which brings us to a total of 8. Carbon has 2 valence electrons in this single bond, and then access to 6 valence electrons in the triple bond, so now carbon is happy as well. And that is the correct structure of HCN. Let's practice another one. Let's draw the formula for HCCl3. Or I will rewrite this as CHCl3, which is usually the form that it is expressed in. So usually it's written in this format, which is a little bit deceiving because it kind of looks like hydrogen would be central, but we know that that can't be true because hydrogen only makes 1 bond. So going back to the number of bonds that each atom typically makes, we know hydrogen only needs 1, carbon needs 4 bonds, and halogens only need 1. So I'm going to place carbon in the center of the molecule. And then I'll place the remaining atoms around it. Then I'm going to count the number of valence electrons that each atom has. Carbon, looking at the periodic table, has 4 valence electrons. Chlorine is in group 7a, so it has 7 valence electrons. And hydrogen is in group 1a, so it has 1 valence electron. Okay, keep in mind that we have 3 chlorines in the formula, so I need to multiply this by 3 to account for that. So there are 21 valence electrons coming from chlorine, 1 from hydrogen, and 4 from carbon. And then I'm going to add all of that up, and we are getting a total of 26 valence electrons. So that's a lot. I'm going to go through and distribute them all just like we did before. So I'm going to start by making a single bond to each atom. That used up 8 valence electrons so far. Hydrogen is happy with the access to 2 valence electrons that it has. Carbon has 2, 4, 6, 8 electrons around it, and it is definitely happy with that situation. But the chlorines right now, not so much. They only have 2 valence electrons each, and they need 6 more. So I'm going to use the remainder of these electrons and distribute them around to chlorines. So chlorine, we've used 8 valence electrons so far. This would be 10, 12, 14, 16, 18, 20, 22, 24, and 26. And now we've used up all of the valence electrons. We've already established that hydrogen and carbon are happy. I'm going to take a look at chlorine right now. It has 2, 4, 6, 8 electrons around it. So it looks like all of the chlorines are happy with that situation as well. And let's do one more example. So this is water. This is a very classic Lewis structure that everybody should be able to draw. So we know that hydrogen wants 1 bond. Oxygen, if you recall, is in group 6A, right here. So it needs to make 2 bonds in order to complete its octet. That means that oxygen is going to be in the center and the hydrogens are going to be around it. Then I'll count the number of valence electrons. And there are 2 hydrogens in the formula, so I need to multiply this by 2 to account for that. And if I add all of that up, that gives me a total of 8 valence electrons. I'm going to start by making a single bond. That used up 4 valence electrons, and the hydrogens are happy with that situation. They already have their duets. So I'm going to distribute the remaining electrons to the oxygen. And when I do that, it looks like this structure is good to go. So oxygen has access to 8 valence electrons, and each of the hydrogen has access to 2 valence electrons. So everybody is happy with that situation. The other thing I wanted to mention is that sometimes different atoms might come up. So let's say, for example, instead of nitrogen, you see phosphorus in a formula. You can handle it much the same way that we did here. Notice that phosphorus is directly under nitrogen on the periodic table. Since they are in the same family, they're going to behave very similarly. So since phosphorus has 5 valence electrons, it also needs to make 3 bonds in order to complete its octet. Likewise, sulfur is going to behave a lot like oxygen. It has 6 valence electrons, so it needs to make 2 bonds to complete its octet. So if you see an atom come up that you are less familiar with, just look at what family it's in and compare it to an atom that you are more familiar with. And that's about it for drawing Lewis structures.